unit axial tensile test. Okay, so this is obtained by, so we are going to carry out unit axial tensile test. So one direction. Okay. So this is P prime. So if we have an element, right? So I'll draw my transformation again. So this is my X, Y, okay, and this is our Z. Okay. So now when we draw our mole circle, not draw, I'm going to sketch it out. So this is our X, this is our Y. So because uniaxial, right? So this is our stress X, right? Stress X is tensile, and the rest are 0. Okay, so we know that stress X is equal to positive, stress Y is equal to 0, shear XY is equal to shear YX, and this is equal to 0. So over here, if now we were to construct mole circle, okay, from an experiment. So this we are now doing we are going to acquire material property from experiment. Okay, so we're going to do a test, and then we start plotting our mole circle, right? So what we will see over here, everything is in tensile, right? So this is our normal stress, this is our shear stress, okay? And we know that over here, this is our point Y, right? And this is our point X, right? So now we start drawing our circle. And we start drawing our circle. So this is 3, 6, upper 3. Because there's no shear stress or whatsoever. Okay, right? So this is our mole. Now, question for you guys. Where is point Z on mole circle? Anyone?
Would it be the same place as point Y?
This is also our point Z. So what you see down here is what? A 3D mole circle or a 3D mole circle analysis also can have what? One circle. That's what I want to expose to you guys. Okay, no, oh, Eugene said 3D mole circle, it's always 3 circles. No, this stage, right? It is just one circle. Okay, and I never ever mentioned a 3D mole circle is a sphere, right? It's never that. Okay, now, so we acquired this from experiment. Okay, now I want you all to watch this. Okay, and I want you to watch and think about this. Okay, so this over here, right? So this distance over here, right? This is our stress U, right? And over here, wait, over here, Cal Max. Can anyone make a relationship between the yield and the tau max for me, please? Anyone? By looking at this diagram. Remember, this is material behavior. Okay. Yes.
Tau max is half the yield.
Okay. So what you will see is our stress yield or tau max is equal to shear yield divided by what? Divided by 2. Okay. So this is known as maximum shear criteria for design for analysis. Okay. Right? And there's a name for it. A very famous person discovered this, not me. How I wish. Okay. I don't discover anything because I watch too much telly nowadays. Okay. Great invention happened before 1960s because after 1960s we have what? We have television. Okay. So this is what we call Tresca yield criteria. Can anyone see how I write the word Tresca? Can anyone say anything about the alphabet that I use? Anyone?
The capital T is a tau.
Huh?
You use
Capital.
the tau.
Yeah, I use tau, right? Because Tresca is spelled Tresca, right? I deliberately put a tau to help you all remember that it's based on what? Based on shear. Deliberately, because a lot of times I test this I give questions to engineers that are applied to work in big companies in the interview. Okay, I can't mention which companies are there, but there are those that you really want to work for them. So they task me to set questions, technical questions like this. Okay, technical questions like this. Okay, now when you go for a job interview, it's not just like I'm a smooth speaker or I can use buzzword, you want to hire me. No. Some companies, yes, but the company that hired me asked me to set questions so that engineers can answer, and the real engineers, the true engineers, can be hired. So I always ask this question. Describe briefly what is Tresca yield criteria based on. And a lot of time they guess. Okay, some guess right. So once they guess right, there's part 2, part 3, like your term test or your exams, okay? And with this, okay, students like you guys will have a deep memory that Tresca is always based on what? Based on shear. Okay, so do things to make yourself remember stuff easily. Okay, now back to where I am. Okay, a lot of storytelling, not very good for teaching. Right. So now so acquire material. Okay, so that is why, in terms of magnitude, right, the shear stress is a lower value. Can you see that? Right? Because of this condition. Right? Because the shearing stress is going to be what? It's going to be half of the yield. So therefore, where am I going with this? Some of you are like, okay, Eugene, where are we going with this? Okay. So remember, right? I wrote down here the importance of tau max. Okay, so that's where we're going to design, right? We're going to design based on shear. Okay, we're going to design. Okay, so that's why when okay, tau max will have a lower magnitude. Okay, therefore the design is based on shear. Okay, now watch this. This is important. Okay, for ductile material only. Remember this, okay? Because this is the next question I'll ask the candidate that is going for interview. Okay, a technical question. Okay, is it true for all materials? And a lot of them say yes. No, for ductile material only. Why? Because only ductile material can withstand what? Shear. Okay, well, I'm going to highlight down here. Brittle material cannot carry shearing stress. at all. Okay, they can't unless you do reinforcement. Like concrete, the only way that they can hold the shear is you reinforce with what? Steel. Yes or no? Okay, that is the only way. Right. So based on that, okay, I'm going to substitute. So using equation 1. Okay, so I'm going to use equation number 1, right? So using equation number 1. So we had a no, that's not. So let me write another thing. So we know that tau max, right, is equal to average stress squared, right, plus by shear zx squared. Okay, so we did write this out before, right? So we did write this out over here. Yeah, we did write this out. Right, we did write this relationship over here, right? So I think I should use this as our equation number 2. Okay, so with equation number 2, okay, which I've just written, okay, substitute equation 1 into equation 2, right? So what we have now is stress max, shearing stress max is equal to stress M, right, over 2 squared, right, and plus by shear xz squared. Okay, so this is now our equation number 3. Nothing difficult. Okay, as I said, this course is not difficult at all. It's an integration. So now we're going to integrate or integration of different topics. So now we know that stress M. Now this is just a general equation. Okay, general equation means I'm only going to be bothered about moment. I'm not concerned with the direction yet. Does not mean it's not important. Later on, we'll put in the direction and then you'll see the full picture. So this will be equal to moment over I multiplied by Y. Right? Right? Because stress M is due to moment. And the shear XZ is equal to T C divided by J, where C is the maximum radius of the shaft. Okay, where's the maximum radius of the shaft? Okay, then after that we are going to substitute stress M and shear XZ into equation number 3. Okay, so we're going to put all of them into equation number 3. Okay, so we have tau max is equal to, so this will be equal to M over 2I Y, right, squared plus by TC over J squared. And then I want you to take note, right? Note, we did this last, I think it was last Friday before our term test. Note that we know the second polar moment of area is equal to 2 multiplied by I. Okay, so from here, we can change our equation to become M over J, right? And then this is Y squared plus by TC over J squared. Okay, and then I'm going to take note for M Y over J to be maximum. Okay, comma. The radius must also, or the Y distance must also be equal to C. What do I mean by that, right? So remember, we have our normal stress, right? So this is our radius. and the maximum radius over here is C. Okay, so on that sense, we can put in that this equation will be equal to MC over J squared plus by TC over J squared.